Okay, you should hear me and I can see you, so we're good to go. And we have slides. Okay, perfect. So, good morning everybody. It's a pleasure to be back in Cluj and Romania, finally, after all this time. My name is Julien. I work for a company called Hugging Face. You may have heard about us, and in the next 30 minutes, I'll try to give you an overview of what Hugging Face is all about, what we stand for, and more importantly, what you can do pretty quickly with our tools. Okay? And when I say pretty quickly, I mean hours, sometimes minutes, definitely not weeks or months or years, which unfortunately seems to be the standard for many machine learning projects. So we like to go fast, we want you to go fast, and this is how we do it. So before we try to accelerate things, we should try and understand what we're starting from. And well, deep learning really kind of started when neural networks, very old technology, was resurrected around 2010, 2012, and finally made useful thanks to the availability of cheap compute. You know, I studied this stuff at the university a century ago, literally, and I was all excited about it. And then at the end of the class, the teacher said, well, yeah, it's pretty cool, but you can't really do anything useful with it. Because back then we had tiny CPUs, and I guess we could train 4 or 5 neuron networks, so totally useless. Now, not the case, so pretty good. Unfortunately, these models are super data hungry, and we need super large data sets. And so we spend a lot of time building those data sets, curating them, labeling them, cleaning them, and instead of doing actual machine learning work, we spend our time writing SQL queries or Spark jobs or Pandas insane code, which I guess is fun up to a point, but that's not really what we wanted to do, right? We wanted to do machine learning. So like I said, cheap compute, GPUs, massively parallel chips, used for something else than 3D gaming, made deep learning possible. But that's all right. But for a long time, it was difficult to grab those chips. I mean, they're expensive. They're not produced in sufficient numbers. And so it was difficult to have the amount of power that you needed, although thanks to the crypto crash, you can buy those things by the metric ton right now. So we have to thank the crypto bros for that. I hope you didn't lose too much money. But the main problem is the tools needed to do all of that stuff are just way too complicated. They were complicated back then, they're still too complicated. I mean, going into the guts of PyTorch and TensorFlow and similar tools is just too much for a lot of folks. If you're a trained machine learning engineer or data scientist, that's okay. But if you're an average developer like me, you know, it's too much, and again, it's not what I wanted. I don't care about tensors. I don't care about channels first or channels last. I couldn't care less, honestly. I don't even want to know. What I want to do is get the job done. I have a business problem, and I want to get to a solution that works in production. Everything in between is just boring, and I don't want to take care of it. I want to move fast, and I'm told machine learning can do it. But unfortunately, given that complexity, a lot of time you don't get to the end. So in recent years, we've seen, I guess, an upgrade of deep learning to what I call deep learning 2.0. That's just me. Maybe it's 1.1. Maybe it's not even that. We'll see. And I guess the main change is the standardization of deep learning architectures to the transformer architecture, which we'll talk about, of course, a little more. And so transformers emerged around 2018 with Google BERT. And not a week goes by now without a new transformer model improving state of the art on text, speech, images, videos, protein structure prediction, and whatnot. It's pretty crazy. Looks like transformers can do pretty much everything. And the even better news is that It looks like the days of building and curating those huge data sets are coming to an end thanks to transfer learning. Transfer learning is a technique where you can start from pre-trained models, right? And again, we'll talk about that. And you can use those models as is, off the shelf, with a couple of lines of code and use them to predict your own data. And sometimes they're just good enough, so you're done. That's it. That's as much machine learning as you're going to do. 2 lines of code. Great. Move on. Sometimes you have very specific domain data. Maybe you do, chemical engineering or genomics or, I don't know, investment trading, etc. And the vocabulary is not necessarily perfectly picked up by the model. So you can train just a little bit more, okay? But the amount of time and data and computing power that you have to dedicate to that is generally 10x or 100x less than doing initial training. So we just move faster. And GPUs are still around, of course, but we see a new category of machine learning hardware popping up. So companies like GraphCore, Habana Labs, Intel, and a whole lot more, who are building hardware accelerators for training and inference. So now it's not just GPUs. We see very effective cost performance ratios out there, and my good friend Cyrus can tell you about the stuff AWS is working on, Inferentia, Trainium, etc., which you can also use with transformers. And the most important thing is this stuff can be performed with developer tools, not expert tools. So anyone in the room who can write 3 lines of Python can do all of this, okay? And you don't need to know what's happening under the hood. You can get to POC stage in hours and do some demos instead of having to go through weeks and weeks of data preparation, training again, etc., etc. So we just accelerate the whole cycle. So zooming in on transformers, we saw it coming for a couple of years, but now we have confirmation that transformers are totally eating deep learning. So traditional architectures like CNNs, LSTMs, RNNs, and all their variations are slowly going away, and they're being displaced and replaced by all those new transformer models for natural language processing and computer vision and speech and everything else. And I listed the most popular here. It's not just us saying it. This is really picked up by industry reports like the State of AI report, the Kaggle Data Science Survey from 2021. And in fact, in the latest State of AI report, 2022, we see confirmation. And we see also that the scope of use cases that transformer models can tackle is growing very quickly. So 2 years ago, 81% of the transformer use cases described in research papers were NLP related, and almost no computer vision, 2%. 2 years later, NLP is still the largest chunk, but it's less than 50% of the total, and you can see the explosion of computer vision and other use cases, right? And of course, this is due to the availability of very efficient computer vision transformer models. So if you thought transformer models and Hugging Face generally are just about NLP, think again. You can solve a lot of different problems with those models. So Hugging Face, who are we? So we're, like I said, we're a company, started in 2016, and we strongly believe in open source. We steward a number of projects. The most popular one is the Transformers library, which lets you work with all those cool models in just a few lines of code. As it happens, it's one of the most popular projects in open source history. It's not me saying it, it's GitHub stars and the community saying it. You can see on this graph, we're on the left, the blue line with the steepest slope, climbing like crazy for a few years now, not stopping. And I'm still surprised to see we grow faster than PyTorch, we grow faster than Keras, we grow faster than all those super nice projects, and we grow faster than Kubernetes, which doesn't make sense to me given the fact that you all seem to be madly in love with Kubernetes. So pretty cool. We love the adoption, and thank you for that. If you've never started the Transformers project, I would appreciate that. We're close to 75K stars, trying to get to 100K, so we could use your help. We also built a website called the Hugging Face Hub, which is where we host models and data sets that you can download for free. All that stuff is open source as well. People call it the Github of machine learning, which I think is an okay analogy. You go to Github to find code and share code. For your projects, well, you can go to the Hugging Face Hub to find models and data sets and share them as well. Okay, and it's what everybody does. I've totally lost hope that this slide would be up to date. It says 72,000 models. I spoke a couple of days ago and updated the slide to 85,000 models, and I was checking just minutes before this, and it looks like we're close to 87,000 models, so it's a lost cause. Looks like we're adding over 500 models every day at the current stage. So yeah, I just can't keep up. So let's say 87,000 pre-trained models for natural language processing and computer vision and speech and reinforcement learning, multimodal models, etc., etc. You can see some of the tasks on the left here. We have over 13,000 data sets ready to go, formatted, that you can download in one line of code. We have over 10,000 organizations, so from Google to Meta, to NVIDIA, to Microsoft, OpenAI, open source projects, university labs, and of course lots of developers and machine learning engineers sharing models on the hub. Day in, day out, we have over 100,000 users. I'm guessing it's way more than that. I should update that number. And I know for a fact we have way, way more than 1 million downloads every single day. So working on this, scaling this is an interesting story in itself. We should tell it sometimes. So if you've never looked at Hugging Face code, I guess this is your first introduction to it, and it's very underwhelming, which is how I like it, right? You're not going to see any virtuoso code, because virtuoso code is difficult, and it's, it stands in the way of getting the job done. Here, I want to classify some text in a simple way, okay? But simple doesn't mean inaccurate, right? Or stupid. I want to do state-of-the-art text classification in the simplest possible way, okay? So starting from the Transformers library, I create a text classification pipeline. I'm actually using zero-shot classification. And the difference between text classification and zero-shot classification is zero-shot classification lets me provide an arbitrary list of labels. I can score that sentence against any label, not just text labels that are part of the training set, okay? Here I'm using a Facebook model called BART. I pass a pretty complex sentence. This comes from Wikipedia, and I want to score it against a bunch of labels. Just pass that stuff to the pipeline, get my results, right? This runs on CPU in milliseconds, okay? So if you need to add text classification to your application, that's it. You don't need a machine learning team, okay? You don't even need to be a machine learning engineer yourself. The pipeline object works for all the task types. You can classify images, you can do text-to-speech, speech-to-text, anything, okay? So this, in a lot of cases, this is as much machine learning as you need. So, of course, this is the NLP world. It's still, like we saw, the biggest chunk of the use cases, but, the world has evolved. And I guess all the rage these days is the text-to-image stuff, right? Diffusion model, and I think this afternoon we have the CTO from Stability AI showing up, so don't miss that. I'm sure it's going to be great. And we built a dedicated library for that called diffusers, and so this lets us work with those super complex models just like that, okay? Creating a pipeline, prompting the model to generate an image based on this, okay? This is a real example that I run, okay, and this is what I got. Okay? And everybody thinks, oh yeah, you generated 1,000 images and you just picked the one that looks okay. And you'll have to trust me, that wasn't the case. I run this code like 2-3 times, and I took this one because I thought it looked cool. But the other ones were pretty good too, right? So that's it, okay? If you need image generation for whatever purpose, it doesn't need to be more complex than that, all right? And yeah, we can do stupid things, right? It's okay to be stupid. So this is still diffusion. It's called in-painting. In-painting means replacing something in the original image with something else. And here I'm using a space. A space is a web app that hosts a model, showcases a model hosted on Hugging Face. And here you can see, this is my face, obviously, and I want to replace the sweater with a Hawaiian shirt, okay? And 3-4 seconds of GPU time, and this is what I get. Okay? Imagine the possibilities. If you work in e-commerce and you need to generate pictures for whatever, right? Product images or just images for your website, right? 5 seconds. No photographer, no model, no lighting, no nothing. 5 seconds. And we're also embarking on very significant collaboration projects. One you may have heard about that completed a few months ago is called Big Science. Big Science started because the machine learning community, and I guess a lot of us, were frustrated by OpenAI closing GPT-3 and slowing down innovation. So we thought, why don't we try and train an alternative to that? And this led to the Bloom model, which you can use on Hugging Face right now for free. This was trained on 1.5 terabytes of text, 350 billion tokens, 43 languages, 16 programming languages. And of course, you can use this for generation, and you can fine-tune it for different things, all for free. And we're pretty proud of that. We've launched another project called Big Code, where I guess we're trying to train a large-scale model for code generation. We've built the data set already. It's called the stack. You can get it. It's 3 terabytes, 30 languages, and comments in 41 natural languages. So yeah, go and try that. Let's see where we land with this, and maybe we can build, again, a free open alternative to those code generation models out there. So Hugging Face in one slide looks like this. On the right-hand side, we start from models and dataset hosted on the hub. And then we can use them as is, like I said, use the pipeline object, very simple. Or we can train them, fine-tune them using transfer learning on our own datasets. You can use our auto-train service if you want to do no-code AutoML, zero programming, just a few clicks. You can do NLP, computer vision, and tabular data. If you want to write code, then you can use the transformers library, which is our main library. You can use accelerate, which lets you control the training loop with more, in more detail, and still makes it easy to do distributed training, multi-GPU, multi-TPU, etc. Diffusers for stable diffusion models. Evaluate, which lets you score any model on any data set in one line of code, as we'll see. Very easy to get a quick sense of how a model performs on whatever test that you have. And Optimum, which is a hardware acceleration library for training and inference that supports chips and products from different vendors we're working with. Spaces is a simple way, like I said, to host your model and showcase them. Do some cool demos for your non-technical users or just for the community instead of running Jupyter notebooks, which nobody really understands. And then, of course, once you have a model you like, you can deploy it anywhere. All that stuff is open source. Go build your containers, use your model server. You're totally free to do that. Or if you want, again, a simple solution, you can use our inference API, which is completely free. It's the free tier, so it's perfect for dev and test. And if you want a production-grade solution, you can use the inference endpoints that let you deploy any model from the hub in just a few clicks, either on AWS or Azure. with auto-scaling and security from public models to completely private models. Okay, so, and we can do all that stuff pretty quick. So, oh yeah, how could I forget? And of course, we have partnerships with our good friends at AWS on Amazon SageMaker. So Hugging Face is a first-party framework on SageMaker, just like PyTorch or TensorFlow, etc. So just bring your code, train, and deploy. And we also made it easy to deploy Hugging Face models on Azure with Hugging Face endpoints. Okay, and yeah, there's someone missing from that slide. So, and I'm tired of asking them to call me. But anybody from Google listening, you've got my phone number. Right? Your users are actually asking us to work with you, so answer the phone, please. All right, demos. I don't have a lot of time, so I'm going to show you one thing, okay? Where's my glasses? All right. Okay, so let's go and look at a few things. So what I did, you know, because, and full disclosure, I worked 6 years for AWS, so that's why I tend to go to the Amazon stuff pretty easily because it saves me time. So I thought, okay, how can I train a model to score product reviews according to star ratings, right? You all know the Amazon star ratings: 1 star, ugly product, 5 stars, amazing product. Okay. So let's start from an Amazon reviews dataset and train a model that predicts star ratings for shoes, okay, shoe reviews. So, and I'll share the link to the actual code to all of this at the end, so don't worry, you can replay everything. I'm taking a few shortcuts. So I started from this dataset here that has God knows how many reviews. It's huge, it's 31 gigabytes. So it's a lot of product reviews from Amazon, and as it happens, it has shoes, right? So, so that's pretty cool. That's a good starting point. So if you're a retailer, right, instead of spending 6 months writing Spark jobs to clean your own data, why don't you just start with this, okay? For POC, that's perfectly fine. This is the English language version. There's a multilingual data set that has French and German and a few more languages. I'm afraid there's no Romanian, but we may have Romanian product reviews somewhere on the hub. I have to say I didn't check. Okay, so starting from this, you know, I extracted shoe reviews and I pushed this data set back to the hub. So this is kind of my own subset for it. Okay, and I removed the columns I didn't want. So I just kept labels and the actual reviews. Okay, that's, I guess, 5 lines of Python here. Not super interesting, so I'm not showing that code. And then I trained a model on this. Okay, and you could use the auto-train service, or if you really want to write code, you could use the transformers library. And let me zoom out because I can't really see anything here. Okay, here we go. And this is the model that I came up with. Okay, so I trained it just for 1 epoch, and I pushed it back to the hub, and I can use it and test it right there. Okay, let's see what this does. So it loads the model on demand and predicts, right? This is actually based on the inference API. Everything I'm showing here is completely free. And we should see a prediction. That's probably a 3-star, 4-star review. Okay, and so I have this model, all that cleaning the data, training the model, all that stuff took maybe, I don't know, 30 minutes. Okay, so that was pretty fast. Okay, so label 3 means it's 4-star. okay? Because as you know, labels need to start at 0, so label 0 means 1 star, label 4 means 5 star. Okay, so I can score the model like that, or if I want to go and, make it a little simpler, I could just go and write a space for it, and I'm a terrible UI developer, and you can certainly build much better looking spaces than this, okay? Right, so that's a 4-star review with 70% confidence. How much code is this? Oh, it's 15 lines of code, and most of the code is actually extracting the label and printing the stars. But again, the UI stuff is always painful to me, right? The prediction is 1 line, the interface is 1 line, the prediction function is just 1 line. Everything is 1 line. That's the way I like it. I wish we could make it 0 lines, but working on that, okay? So that's spaces. Write this stuff. I use Gradio. You can use Streamlit as well. Test it on your local machine when it works. Create a space repository on the hub. Push it there, and it fires up a container. And you can just run this, right? And we see the model that I use here. You could also host it for real, okay? So let's say we want to create a production endpoint for this. So we'll just grab the model from the hub, give it a name, decide where we want to host it, how we want to host it, CPU, GPU, and the bigger GPUs are coming soon, so you'll be able to host on multiple A100s. Okay. That's going to be a little more expensive than a small CPU, but that can be helped. You can do auto scaling if you want, etc., etc. And you can decide if this needs to be public, which means open to the world. Anyone on the internet can call the endpoint. Protected means it's public with token authentication. And private means it's not open to the world, and you can only call it from your own AWS or Azure account, right? So we set up private connectivity between your account and our account, and so you can call the model without going through the public internet. So if you have strong compliance needs, if you work for a bank, etc., that's the kind of stuff you need. So it takes a few minutes to set up, so I've already done this. Unless my colleagues deleted it, I should have, yes, I should have it here. They do that sometimes. And yeah, okay, so we could test it here, but I guess what we want to do is really try it for real, just like this. Okay, so I'm on my local machine here. So here's the endpoint URL, my authentication token, and the rest is just HTTP requests, okay? There you go. So deploying models is generally very, very difficult, but not here, right? And this will auto-scale and be secured, etc. I have a few minutes left. There's one more thing I want to show you. So those models are generally pretty big models, right? I mean, if we look at this model that I used, and this is it's a distilled-BERT model, so it's already kind of a smaller model. But as you can see here, it's 268 megabytes, right? Which is not big for a transformer model. I mean, you have multi-gigabyte models. So prediction latency and generally model size can be an issue. And that's why we work a lot to optimize those models, shrink them, make them faster. And this is an example of doing this. Maybe I should zoom in a little bit. Yes. This is an example of doing this with ONNX. Okay, so sure, you can go and grab the ONNX tools, or you can work with our integration inside the Optimum library, which, like I said, is our library dedicated to acceleration. So starting from the same model, okay, and loading the same model and the same data set that I showed you before, okay. First, we evaluate the baseline model, right? And I'm using the evaluate library to score the accuracy of this model on this data set, right? And I copied the output to a terminal to make it a little simpler to read. Okay, so accuracy is this, and it takes 153 seconds to score those 10,000 reviews. Okay, this is running on a CPU instance, right, on AWS. So 153 seconds. So that's my baseline, right? And then I can export the model to ONNX, and this is really what it takes. Okay, load the model, save it as an ONNX model. Job done. Okay. And then I can evaluate it again. And now I'm gone from 153 seconds to 110 seconds. So that's already just goes to show the ONNX runtime is a better runtime than using vanilla PyTorch, right? So just exporting the model saves you about 20%. And then we can go one step further. We can actually apply ONNX optimization, which is as difficult as this, okay? Just optimizing the model and saving it. And this will do all kinds of weird things, which I don't have time to discuss. You can dive into the ONNX optimizer, okay? Then if I evaluate that again, now I'm down to 98 seconds, so I gained another 10%. And you can see accuracy doesn't move, right? I'm not hurting accuracy. And finally, I can go all in and do quantization, replacing all the 32-bit parameters in the model with 8-bit integers, not floating points. And this is as difficult as this, okay? And now I'm down to 58 seconds. Accuracy didn't move, okay? So we reduced latency by 2.6x with simple Python code, and the model has gone to 260 megs, 230 megs. Okay? What is there to understand? Just apply the code, enjoy the results, right? Which is what I like. Get results. So that's a really quick tour of the Hugging Face family. Final slide. If you want to get started, I would recommend checking out the tasks page to understand all those different task types that you can do with transformers. The Hugging Face course, which takes you from I know nothing to I can do all of this and more. Of course, our repos on GitHub, my own repos where you'll find all that code and more on GitLab. If you want to stay in touch, find me on Twitter while Twitter is still there. I'm on Medium, YouTube, LinkedIn. Happy to connect. Yeah, Elon said yesterday they might die in 6 months, so I don't know. Let's see. It's going to be a fun thing to watch. And if your company needs help with transformers and all of this, ping me. We can help you with engineering support, private deployments, and we can bring you in production in weeks. We'll go as fast as you can. Generally, you're the limiting factor, and we try to help you get there, okay? Well, that's really it for me. Thank you so much to Kodiaks for inviting me, Vlad, everybody else. It's an amazing team. Thank you so much for showing up this morning, and I wish you a very good conference today. Thank you very much.